December 1970. The Mediterranean Sea. The aircraft carrier USS Saratoga was conducting a full-power run. In the naval chessboard of the Cold War, the carrier was the queen, massive, heavily defended, and capable of 30 knots. No submarine could catch a carrier at full sprint. The math simply didn't allow it. Until the sonar operators on the Saratoga heard a sound that defied physics. Contact designated Sierra 1, submerged, closing from astern, speed estimate 44 knots. Repeat, 44 knots. The captain of the Saratoga demanded a recount. Submarines did not move at 44 knots. Submarines moved at 25 knots. To move a submerged hull at that speed would require engine power that existed only in science fiction. But the contact was real. It overtook the carrier. It circled the carrier. And then, with a burst of speed that registered as a screech on the sonar tapes, it vanished into the deep. The vessel was K-162, Project 661. NATO called it the Alfa-class. It was a titanium beast that held the world speed record. The Pentagon panicked, but intelligence analysts offered a sliver of hope. They argued that K-162 was a unicorn, a single, ruinously expensive prototype that the Soviets could never afford to replicate. They believed the threat was an anomaly. They were wrong. Satellite reconnaissance over the Severodinsk shipyards soon revealed the terrifying truth. The Soviets weren't stopping with the prototype. They were building a production line, a new class of hunter-killers, smaller, more agile, and armed with the same titanium skin. It was Project 705, the Lyra, known to NATO simply as the Alpha. The Papa proved it was possible. The Alpha proved they were coming for us. This is not a story about who built the faster ship. It is an analysis of why the United States Navy looked at the most advanced piece of naval engineering on Earth and decided that the smartest move was to do nothing. The history of the Cold War is frequently reduced to a binary contest of ideologies. Yet beneath the surface of the world's oceans, it was a clash of fundamentally divergent engineering philosophies. On one side stood the Soviet design bureau Malakit. Their philosophy was hard specification, maximum speed, maximum depth, maximum automation. They believed that superior physics would win the war. On the other side stood the United States Naval Reactors Office, commanded by the uncompromising Admiral Hyman G. Rickover. His philosophy was soft specification, reliability, acoustic stealth, and logistics. He believed that a weapon system's effectiveness is determined not by its peak performance in a sea trial, but by its sustained availability in a theater of war. In this briefing, we will deconstruct the engineering of the Alfa-class. We will examine the metallurgy of its titanium hull, the thermodynamics of its lead-bismuth reactor, and the fatal flaw that turned these technological marvels into radioactive tombs. We will analyze how the appearance of this super sub rendered the existing American torpedo inventory obsolete overnight, creating a vulnerability window where NATO carriers were defenseless against underwater interception. And finally, we will reveal why the American response, the Los Angeles-class submarine, was designed not to outrun the Alpha, but to outlast it. We will demonstrate how boring engineering defeated radical engineering.
The Alpha was designed to win a sprint. The Americans were designing for a marathon. Welcome to the edge of the impossible. This is Apex Engineering. To understand the magnitude of the Alpha crisis, we must first calibrate the baseline of 1960s anti-submarine warfare. The tactical assumption was the closing speed equation. In a hunter-killer scenario, the weapon must possess a significant speed advantage over the target to account for maneuvering. If a target moves at 25 knots, the torpedo must move at 40 knots to successfully intercept it before running out of fuel. For 2 decades, this equation favored NATO. The Soviet submarine fleet was composed largely of diesel-electric boats and first-generation nuclear vessels like the November-class, which struggled to break 30 knots and generated immense noise while doing so. The primary U.S. weapon was the Mark 37 Mod 00. It was an electrically propelled, wire-guided cylinder with a top speed of 26 knots. Against a diesel boat moving at 6 knots, it was lethal. Against a November class moving at 28 knots, it was marginal. When the Alpha entered service, the equation collapsed. If a U.S. submarine fired a Mark 37 at a fleeing Alpha, the torpedo would not just fail to catch the target would actually pull away from the weapon. This was not a theoretical gap. It was a hard counter to the entire American order of battle. The Pentagon's war games revealed a catastrophic vulnerability. The Alpha was not designed for long patrols. It was an interceptor. Its mission profile was to sit in port, wait for a satellite cue indicating a U.S. carrier battle group, and then sprint into the Atlantic at speeds no Western vessel could match. Once in the battle space, the Alpha's agility was equally defying. Acoustic analysts noted that the vessel could accelerate from 6 knots to 40 knots in under 60 seconds. It possessed the thrust-to-weight ratio of a fighter aircraft. This acceleration allowed for a maneuver that American crews came to dread: the Crazy Ivan. A conventional submarine requires significant time and distance to turn. The Alpha could execute a high G bank, reversing its course in a radius so tight it defied hydrodynamic logic. In a close-quarters dogfight, this allowed the Alpha to check its baffles, the blind spot behind the screw, and fire a snapshot torpedo before the American submarine could bring its tubes to bear. The intelligence community was paralyzed. They were staring at a vessel that was half the displacement of a U.S. sub, yet twice as fast. It was as if the Soviets had taken a tank engine and mounted it inside a Ferrari. The question plaguing the Office of Naval Intelligence was simple. How? How could a nation that struggled to build reliable refrigerators produce a submarine that defied hydrodynamic drag? The answer lay in 2 decisions that Western engineers considered suicidal. The Soviets had abandoned steel, and they had abandoned water.
Naval architecture is a war against weight. To make a submarine go faster, you need a larger reactor. A larger reactor requires a larger hull. A larger hull creates more drag, which requires an even larger reactor to overcome. This is the spiral of diminishing returns that limits conventional submarine speeds to roughly 30 knots. To break this cycle, the Soviet Malachit Bureau realized they needed to fundamentally alter the density of the vessel. They needed a material that was lighter than steel, but strong enough to withstand the pressure of the deep ocean. They chose titanium. Titanium is the holy grail of structural engineering. It is 40% stronger than steel for the same weight. It is non-magnetic, drastically reducing the vessel's signature on the magnetic anomaly detectors used by American patrol aircraft. And it is impervious to corrosion. But there is a reason the U.S. Navy did not use it. Titanium is a nightmare to work with. At welding temperatures, titanium becomes highly reactive. It possesses a chemical affinity for oxygen, nitrogen, and hydrogen. If a welder attempts to join two plates of titanium in an open shipyard environment, the metal will absorb these atmospheric gases instantly. The result is hydrogen embrittlement. The weld might look perfect to the naked eye, but at a molecular level, it has the structural integrity of glass. Under the pressure of a deep dive, the hull would shatter. To build the Alpha, the Soviet Union had to construct the largest hermetically sealed environments on Earth. Severodvinsk Shipyard, Building Number 42, status, restricted, atmosphere, argon. Building 42 was a cathedral of inert gas. The entire assembly hall was purged from air and flooded with high-purity argon. The workers inside could not breathe the air they stood in. They were encased in pressurized suits, resembling cosmonauts, tethered to external oxygen supplies as they welded the hull sections of the Project 705. The complexity of this process was staggering. A single microscopic leak in a welder's suit meant death. A single impurity in the argon mix meant the hull section had to be scrapped. The rejection rate was astronomical. The cost was ruinous. The titanium sponge required for the fleet was so expensive and the manufacturing process so laborious that the predecessor class, the Papa, earned a cynical nickname within the Soviet Admiralty, the Golden Fish. They joked that it would have been cheaper to construct the hull from solid gold. But the result was undeniable. The Alpha displaced only 2,300 tons surfaced. This was less than half the weight of the American Los Angeles class. With a hull capable of diving to depths the West could only estimate, the Alpha could operate in a thermal layer of the ocean that U.S. torpedoes struggled to penetrate. But a light hull was only half the equation. To achieve 40 knots, the Alpha needed an engine with power density that exceeded anything in the Western inventory. They needed a reactor that ran hotter, faster, and more aggressively than physics should allow. They needed liquid metal. Every nuclear reactor in the U.S. Navy, from the Nautilus to the modern Virginia class, is a pressurized water reactor, or PWR. The concept is simple. You split uranium atoms to generate heat. You pump water through the core to absorb that heat. You use that hot water to boil a secondary loop of water into steam, which spins a turbine. Water is safe. But as a coolant, water has two significant limitations. First, it is a poor conductor of heat compared to metal. Second, it boils at 100 degrees Celsius. To prevent the water in a reactor from turning into steam inside the core, it must be kept under immense pressure, over 2,000 pounds per square inch. This necessitates heavy, thick-walled piping and massive pressure vessels. A PWR is inherently heavy. The Soviet engineers calculated that a water reactor would never fit inside the 2,300-ton displacement limit of the Alpha. They needed a coolant that could absorb heat 10 times faster than water, without the need for heavy pressurization. Their solution was the OK550 reactor. The coolant was not water. It was a molten alloy of lead and bismuth. The physics of lead-bismuth eutectic, or LBE, are seductive. Lead-bismuth has a boiling point of 1,670 degrees Celsius.
This meant the reactor could operate at extremely high temperatures without the coolant flashing into steam. Consequently, the primary loop did not need to be highly pressurized. The heavy steel piping required for a U.S. reactor could be replaced with thinner, lighter components. More importantly, molten metal moves heat with terrifying efficiency. In the Alpha's lead-bismuth core, the thermal conductivity was so high that the reactor effectively had no thermal lag. The captain could order full power, and the reactor would respond instantly. This was the secret to the Alpha's acceleration. It could go from idle to full thrust in the time it took U.S. Submarine to verify the order. Combined with the titanium hull, the LBE reactor gave the Alpha a power-to-weight ratio that was unmatched in maritime history. It was a technological triumph. But in their pursuit of the perfect thermodynamic cycle, the Soviet designers had overlooked a critical operational flaw, a flaw that would not show up in the equations of a physics textbook, but would reveal itself in the brutal reality of the Arctic winter. Water, when the reactor is shut down, simply cools. It remains a liquid. Lead-bismuth, when it cools below 125 degrees Celsius, turns into a solid rock.
In Washington, the specifications of the Alpha were laid before Admiral Hyman G. Rickover. Rickover was a man of legendary abrasive intellect. As the director of naval reactors, he held absolute authority over every aspect of American nuclear propulsion. He was the gatekeeper. The panic in the Pentagon was pushing for a symmetric response. The logic was linear. The Soviets have a 40-knot titanium sub. We need a 45-knot titanium sub. We need to close the kinematic gap. Rickover looked at the intelligence on the lead-bismuth reactor and the titanium welding, and he famously demurred. He did not order a crash program to copy the Alpha. Instead, he validated a different approach. Rickover knew something the Soviet designers were about to learn the hard way. The U.S. Navy had already built a liquid metal submarine. In 1957, the USS Seawolf, the second nuclear submarine in history, was launched with a sodium-cooled reactor. It was designed for the same reasons as the Alpha: higher efficiency and greater power density. It was a disaster. USS Seawolf, sea trials, superheater failure, sodium leak detected in steam generator loop, coolant activity critical. Sodium is highly reactive. When it leaks and contacts water, it explodes. The Seawolf was plagued by superheater leaks and corrosion issues that kept the vessel constantly on the verge of a catastrophic thermal event. In 1958, Rickover ordered the sodium reactor cut out of the hull and replaced with a standard pressurized water reactor. His verdict was absolute. Reactive coolants have no place in a warship. Rickover understood that a combat vessel is not a laboratory experiment. It is a home for 100 men, operating in a hostile environment, thousands of miles from support. Complexity is the enemy of survivability. He identified the Alpha's Achilles heel immediately: the freezing problem. To keep the lead-bismuth molten, the Alpha's reactor could never be turned off. Even when docked in port, the reactor had to run at low power to maintain the 125-degree temperature threshold. This created a logistical chain that tethered the supersub to the pier. The Alpha was dependent on the crumbling infrastructure of remote Soviet naval bases. If the shore steam failed during a maintenance cycle, the submarine died. Rickover's doctrine was clear. The United States would not build a port queen. The goal of the American Navy was global power projection. However, the tactical problem remained. The Alpha was still out there. It was still faster than any torpedo in the U.S. inventory. Reliability wouldn't matter if the American subs were destroyed before the fight began. The U.S. Navy needed a solution that didn't involve exotic metals or dangerous coolants. They needed a way to kill a 40-knot target with a 25-knot platform. The answer lay in a new doctrine: asymmetric warfare. If you cannot outrun the enemy, you must ensure he never sees you.
As the U.S. Navy committed to its conventional reliability, the Soviet wonder weapon began to self-destruct. The fragility of the Project 705 design was not hypothetical. It was demonstrated with devastating finality aboard the lead ship of the class, K-64. Shortly after commissioning, K-64 suffered a leak in the primary cooling loop. The lead-bismuth level dropped, the flow stopped, and as the temperature gauge fell past 125 degrees, the physics of the eutectic alloy took over. The liquid metal inside the reactor core froze. In a matter of hours, the heart of the submarine transformed into a solid, immovable block of radioactive metal. The fuel rods were entombed. The control rods were seized. There was no way to thaw it. There was no way to repair it. The Soviet Navy towed the brand-new billion-ruble vessel back to Severodvinsk. They sawed the bow off for training usage and towed the reactor compartment out to sea to scuttle it. The most advanced submarine on Earth had been defeated not by an American torpedo, but by a drop in temperature. The disaster was not an isolated incident. The requirement to keep the ships hot at all times overwhelmed the Soviet fragile infrastructure. Shore steam lines would freeze and burst in the Arctic winter, forcing crews to run the reactors dangerously hard just to keep the coolant liquid. Then came the catastrophe on K-123. Leak in the steam generator, radioactive coolant entering the reactor compartment. All hands mask up. 2 tons of molten lead-bismuth sprayed into the engineering spaces. It didn't just irradiate the compartment. As it cooled, it welded the machinery shut. The cleanup took 10 years. The Alpha was proving Rickover's thesis with every accident. It was a Formula One car trying to survive in a demolition derby. It was fast, but it was too fragile for war. Meanwhile, the Americans were finalizing their answer. It wasn't a faster submarine, it was a faster bullet. The American response to the Alpha was to double down on the Los Angeles-class submarine. Compared to the Alpha, the 688 was boring. It was built of high-tensile steel, not titanium. It used a standard pressurized water reactor, not liquid metal. Its top speed was classified as 30+ knots, fast, but technically slower than the Soviet sprint speed. But the Los Angeles possessed the one attribute that the Alpha lacked: stealth. The Alpha was fast, but it was deafening. The flow noise of water rushing over the hull at 40 knots, combined with the pump noise of the liquid metal reactor, made the Alpha light up passive sonar screens across the entire North Atlantic. The Los Angeles class was a hole in the water. Its machinery was raft-mounted to isolate vibration. Its hull was coated in anechoic tiles. A 688 patrolling at 5 knots was virtually undetectable. The U.S. doctrine shifted to first look, first shot, first kill. The plan was not to chase the Alpha. The plan was to ambush it. But an ambush requires a weapon that can finish the job. The Mark 37 was retired. In its place, the Navy deployed the Mark 48. The Mark 48 was the true Alpha killer. It was a heavyweight monster fueled by Autofuel II. It used a swashplate piston engine
that allowed it to scream through the water at 55 knots, deep enough and fast enough to run down the titanium fugitive. Throughout the 1980s, this capability was refined into ADCAP, Advanced Capability. Engineers hardened the guidance wire and rewrote the logic software. The ADCAP didn't just home in on sound, it anticipated maneuvering. If an Alpha attempted a high G turn, the ADCAP's digital brain would recognize the geometry, adjust its intercept trajectory, and reacquire the target. The math had been corrected. Even if the Alpha ran at 42 knots, the Mark 48 closed the distance at a relative speed of over 10 knots. The Alpha could not outrun the weapon, and because the Alpha was so loud, it would be detected at 50 miles, while the silent Los Angeles could approach to within 15 miles before firing. The Soviet pilot would be dead before he ever saw the American submarine.
The Cold War underwater arms race is a definitive case study in the tension between theoretical performance and operational reality. The Soviet Union built 7 Alfa-class submarines. They were technological marvels, pushing the boundaries of metallurgy and thermodynamics. But they were strategic failures. They spent the vast majority of their service lives tied to the pier, broken by the complexity of their own systems. They were a weapon that worked perfectly on paper, but failed in the water. The United States built 62 Los Angeles-class submarines. They were conservative, reliable, and mass-producible. They became the backbone of Western naval dominance for 40 years. The legacy of the Alpha is a lesson for every engineer and strategist. It is tempting to chase the apex of performance, to use the most exotic materials, the highest temperatures, and the most radical designs. But war is not won by the device that has the highest specs. It is won by the device that shows up. The U.S. Navy won the underwater Cold War not by being faster, but by being smarter. They realized that in the unforgiving environment of the deep ocean, the most powerful capability of all is reliability. Sometimes the most advanced move is simply to build a machine that works.